Hi friends, in this video we are going to discuss about the previous gate question. Let's see the question. The torque angle of a synchronous machine. The torque angle of a synchronous machine operating from a constant bus voltage is usually defined as the space angle between. Now tell me, what is actually our question? What is the torque angle? What is the torque angle? Let's see, generally in our synchronous machine, for example, I am taking a synchronous machine which is sail in pole. I am taking a synchronous machine. For example, this is my synchronous machine. For example, this is my synchronous machine. For example, this is my rotor flux axis. For example, this is my rotor MMF. This is my rotor MMF axis. And for example, I'm taking here, this is my stator MMF. This is my stator MMF. The resultant of stator MMF and rotor MMF is generally taken as air gap flux or resultant flux. Yeah. For example, this is my rotor MMF and this is my stator MMF, and this is my air gap flux or resultant flux. Yeah, now tell me, what is torque angle? The torque angle lambda is the space angle between stator MMF and rotor MMF. Lambda is the torque angle. The torque angle is the space angle between the stator MMF and rotor MMF is 100% correct answer. Sir, what about this? What is this? The angle between the rotor MMF and the resultant flux. The rotor MMF and resultant flux angle is delta, is called load angle. Yeah, this is the load angle delta and this is the torque angle lambda. So actually our question is, what is torque angle? Torque angle is the angle between stator MMF and the rotor MMF. This is our answer. Okay, let's see the next question. Let's see the figure. The figure depicts the load characteristics. The figure depicts the load characteristics of an isolated three-phase alternator running at constant speed. This is the figure which depicts the load characteristics of an alternator which running at constant speed. Yeah, match the following set of operating conditions. Match the following sets of operating conditions with given characteristics. Like, tell me, what are the characteristics represent us? What these characteristics gives us? Yeah, tell me, what is this represents? This represents the constant excitation with the zero power factor leading. Constant excitation with zero power factor leading. This is more leading, that's why I am taking zero power factor leading. This is also the Q. This Q represents us constant excitation. This is zero power factor leading, but this is less than zero power factor leading, but not unity power factor. That's why this represents non-zero power factor leading. These two are for constant excitation, zero power factor leading and non-zero power factor leading. Yeah. Okay. What about remaining two? What about these two? let's see, this is for constant terminal voltage. This is for constant terminal voltage, constant terminal voltage, constant terminal voltage. Zero power factor leading or non-zero power factor leading. This is non-zero power factor leading and this is the zero power factor leading. More leading, less leading. That's why constant terminal voltage, non-zero power factor leading. Non-zero power factor leading. This represents constant power factor, constant terminal voltage, non-zero power factor leading. Yeah, and last one, what it represents? This represents constant terminal voltage, constant terminal voltage, constant terminal voltage, zero power factor leading, zero power factor leading. These are the representation of this graph. So what is generally the P zero power factor leading? And this is one non-zero power factor leading. These two for constant excitation, these two for constant terminal voltage. Right? Right, sir, let's see the next question. A three-phase alternator has negligible stator resistance. Short circuit test conducted on this alternator. At a particular speed, a field current of IF is required to drive the rated armature current. If the speed of the alternator reduced to half, then the field current required to maintain rated armature current is. Yeah, let's see the question. Let's see, generally we know E is equals to V plus IA into XS actually. When the resistance is neglected, armature resistance is neglected. And they said under short-circuited condition, V is equals to 0 and IA is equals to ISE. Of course, that is our armature current under short-circuited condition. Now tell me what is the answer. E is equals to ISE into XS. So ISE, nothing but IA is equals to E by XS. But he said that my speed reduced to half. When speed reduced to half, the frequency also reduced to half. When frequency reduced to half, we know EMF directly proportional to frequency and XS also directly proportional to frequency. So, our EMF reduced to half, and our XS reduced to half. Because the speed reduces off, so frequency off, so EMF off and XS also off. Then tell me, what about this armature current? Let's tell me E is the E by 2 and XS is the XS by 2. This 2 gets cancelled. Again E by XS. Nothing but there is no changes in this armature current. There is no changes in this armature current even though the speed reduced to half. Even though the speed reduced to half, the armature current is rated current only again and again. That's why the armature current is independent of speed. The armature current is independent of speed. The short circuit current is independent of speed under short circuit condition. Under short circuit condition, the armature current or short circuit current is independent of speed. So the armature current is again rated current only. That's why, what is our answer now? What is the field current required to maintain rated armature current? The same field current, or double the field current, or half of the field current, or insufficient data they given? So tell me, sir, what is the answer? Yeah, no need to change the field current because Before and after reduction of speed, the armature current is rated only. That's why our answer is same field current required. Right? Same field current required. Okay, sir. Next question. Synchronous motor operates at 0.8 power factor lagging. 0.8 power factor lagging. If the field current of the motor is continuously increased, then what happened to armature current and power factor? The question is that, what about armature current and what about power factor? What about armature current and what about power factor? Let's see what is the answer. So first we have to draw the V-cos and inverted V-cos for motor. Let's see how they are. Let's see. For example, this is my field current. For example, this is my armature current. For example, this is at normal excitation condition. At normal excitation, some field current. If a field current increases, over excitation. If field current decreases, under excitation. If a field current decreases, under excitation. Right? Yeah. So first, armature current to the field current is nothing but V cos. Under normal excitation, the armature current is minimum. Under normal excitation, the armature current is minimum. Under normal excitation, the armature current is minimum. When excitation increases in either direction, the armature current also increases. This is the V cos. What about inverted V cos? Inverted V cos. Let's see the inverted V cos. This is, for example, field current, and this is, for example, power factor. For example, this is normal excitation. When field current increases, over excitation. When field current decreases, under excitation. At normal excitation, power factor is unity. When excitation decreases or increases, the power factor reduces. Yeah, this is well known. But now the thing is that, which is leading, which is lagging? Synchronous motor under over excitation condition leading, under excitation condition lagging, under excitation lagging, over excitation leading. Now tell me, where my synchronous motor operating? At 0.8 power factor lagging. At 0.8 power factor lagging, nothing but, for example, here my synchronous motor is operating. For example, here my synchronous motor is operating. Here my synchronous motor is operating. If the field current of the motor is continuously increased, this is my field current. From here, my field current is continuously increased. My field current is continuously increased. Then what happened to armature current? Tell me, what happened to armature current? The armature current first from here, first reduces to minimum. What is the answer? My armature current reduces to minimum, then reduces to minimum. From here reduces to minimum, then increases. My armature current first reduces to minimum, then increases. This is the answer for armature current. What about power factor? Actually, I'm here at 0.8 lagging. From here, they are increasing my field current. Nothing but first the power factor increases to unity. This is unity power factor, right? Increases to unity. Then after increases to unity, then decreases. This is our answer. Yeah, my synchronous motor operating under lagging load, 0.8 lagging, continuously field current increases. So armature current reduces to minimum, then increases. Power factor increases to maximum, then decreases. This is our answers for this question. Let's see the next question. Two 550 kVA alternators, operate in parallel to supply the following loads. One is 250 kilowatts at 0.95 power factor lagging. Other one 100 kilowatts at 0.8 power factor leading. Yeah. One machine supplying 200 kilowatts at 0.8 power factor. One machine supply at 200 kilowatts at 0.9 power factor. The power factor of the other machine is. This is the question, right? Let's see. First, take the first one. First one they given like this. This is 250 kilowatts, and we don't know kVA of this one, and we have this power factor 0.95 lagging. Then how we can get this kVA? How we can get? Generally, the cos pi is equals to adjacent by hypotenuse, adjacent divided by hypotenuse. So now tell me, what is our kVA? kVA is equals to 250 by power factor cos pi. What is my cos pi? 0.95. What is the angle at cos of 0.95? At cos inverse of 0.95. This is my kVA at an angle. Similarly, for second machine, kVA is equals to, tell me what is for second machine? 100 divided by 0.8 at an angle of cos inverse of 0.8 at an angle of cos inverse of 0.8. If we calculated these two, then we can get this kVA. 250 minus J82.17. We can get this formula from the solving this one. We can get this kVA 250 minus J82.17. By solving this, we can get this kVA is equals to 100 plus J75. 100 plus J75 and 250 minus J82.17. But they given one machine supplying 200 kilowatts at 0.9 power factor lagging. One machine supplying at 200 kilowatts 0.9 power factor. For that, what is the answer? For that, the kVA, the supplied kVA is equals to 200 divided by 0.9 at an angle cos inverse of 0.9. At an angle cos inverse of 0.9. If we calculated that, then we can get this kVA. This kVA is equals to 200 minus J96.86. This is for first machine. This is for second machine. This is for first load. Then what is the load supplied by the second machine? According to power conservation law, the load should be equals to supply. Demand should be equals to supply, right? According to that power conservation law, the kVA1 plus kVA2 should be equals to kVA 1 plus kVA 2 of the supply should be equals to the load of the first one plus load shared by the second one. Nothing but 250 minus J 82.17 plus 100 plus J 75 is equals to 200 minus J 96.86 plus the load shared by second alternator. If we calculate this value after by solution of this one, by solving this equation, we can get the load shared by second alternator is equals to, the load shared by second alternator is equals to 174.65 at an angle 30.814 degrees. Here positive, not negative. Positive, not negative. Yeah. The load shared by the second alternator 174.65 at an angle 30.814 degrees. 814 degrees. Then tell me, the positive sign represents just leading load. The positive sign represents just leading load. So what is our power factor? Power factor nothing but cos pi, nothing but cos of 30.814. 30.814. If you calculate this cos of 30.814, then you can get, these two are not same actually. One is 0.89 leading and another one is 0.85 leading. So what do you get? If you calculate cos of 30.819, then you can get around 0.85 leading, or this exact value 0.8588 leading. 0.8588 leading. So what I done actually, here I calculated the apparent power kVA for first machine, similarly for second machine, similarly first machine load sharing, and the next the second machine load sharing in terms of magnitude and angle. After solving this one, we can get this value with an angle. So power factor is equal to cos of this angle. Then we can get this is the answer, and 0.85 leading is the correct answer. Yeah. Let's see the next question. What is here? Synchronous motor on load. Draw a current at a leading power factor angle phi. Leading power factor angle phi. If the internal power factor angle, which is phase angle between the excitation EMF and the current. Excitation EMF and the current in time phasor diagram is psi. Simply, the internal angle is psi and the power factor angle is phi. Next, then the air gap excitation MMF lags the armature MMF by. Air gap excitation MMF lags the armature MMF by. This is our question. Actually, I will give you for an alternator first of all. For alternator, for example, this is induced EMF E, and for example, this is my main field flux, excitation flux phi m. Main field flux, excitation flux phi m. And generally, this is the supply voltage V, for example, terminal voltage V, induced voltage E. The angle between these two is called as delta. But for leading load, the armature current for leading load, for example, this is my armature current for leading load with an angle phi. And angle between EMF and armature current is psi. The armature current and induced EMF, the angle between these two is the psi. Now tell me, where is my main field flux? This is my main field flux. Where is my armature flux? This is my armature flux. What is the angle between them? What is the angle between these two? The angle between these two, actually this is 90 degrees. This is 90 degrees. Actually this is 90 degrees and this is psi. So the angle between main field flux or excitation flux and armature flux is 90 plus psi for alternator. This is for alternator. Actually this is for alternator. As well as the angle between main field flux and armature flux for motor, its value 90 minus psi. For motor, its value 90 minus psi. Just reverse. Actually, what is psi? The angle between EMF and armature current. And they asked that armature and excitation MMF, the angle between those two. Those two, actually in alternator 90 plus psi. But in synchronous motor, its value 90 minus psi. This is the answer for this question. Say 90 minus psi is 100% correct answer. Right, next question. Distribution factor. We have to find out KD. Distribution factor for a 36 slot with a 3-phase 8-pole winding. 36 slot, number of slots 36, number of poles 8, and they given it is a 3-phase machine, and also they given M beta, the phase spread is 120 degrees. The phase spread is 120 degrees. Let's check it. Is it the concentrated winding or distributed winding or integral slot winding or fractional slot winding? First of all, let's check it. What is the value of M, the phase belt? Phase belt M is equals to slots per pole per phase. Slots per pole per phase. So what is the answer? 36 by 8 by 3. 36 by 8 by 3. Nothing but around 12 by 8. 12 by 8 can be written as 4 into 3 divided by 4 into 2. 4 into 3 divided by 4 into 2. This 3 by 2 is called characteristics ratio. This 3 by 2 is called characteristics ratio. Characteristics ratio SK by PK. The characteristics ratio SK by PK. This is the fractional slot winding. This is not integral slot winding. For fractional slot winding, KD is equals to, what is the answer? For fractional slot winding, KD is equals to sine M beta by 2 divided by SK into sine M beta by 2SK. Sine M beta by 2SK. Actually, this is the formula. Let's solve it. Sine M beta by 2, nothing but sine 120 by 2, sine 60 divided by SK is the 3 and sine 120 divided by 2 into 3. 120 divided by 2 into 3. Nothing but sine 60 degrees divided by 3 into sine 120 by 6. Nothing but sine 20. If you calculate this value, then we can get the answer 0.844. 0.844. See here, this is the formula for fractional slot winding. Is very important. Okay, next question. In figure, the characteristics that corresponds to the variation of excess synchronous reactance, variation of excess of synchronous motor with the field current is. Yeah, the relation between synchronous reactance and field current. Generally, when field current increases, actually the EMF also increases, but it is saturated. When field current increases, the armature current increases continuously. Nothing but the excess is equals to E by IA, EMF by armature current. Simply, the EMF increases, but after that saturated. But my armature current is always increasing in manner linearly. Nothing but initially the EMF increases and current also increases. So the impedance is mostly constant. But after some time, our EMF saturated, nothing but EMF increasing is not in linear. But armature current is increasing. Nothing but denominator is increasing. So the excess value decreasing. Yes or no? Because after saturation, even though after saturation, our armature current is increasing. Armature current is increasing, so the excess value decreases. Excess value decreases. So what the curve? The second curve. Actually, this curve represents the synchronous reactance. Sir, why it is decreasing? Because after saturation, there is no changes. There is no changes in EMF, but the armature current is increasing, so the synchronous reactance is decreasing. Synchronous reactance decreasing. This is simply about the relation between field current and synchronous reactance. Alright, sir, next one. Next, during the hunting of synchronous motor. During the hunting of synchronous motor, which of the following is correct answer? Tell me first one, option A, negative sequence currents are generated. Is it correct? Let's see. Harmonics are developed in the armature. Is it? Let's see. Damper bar produces torque. Damper bar produces torque. Next one, field excitation increases. Is it correct? No. Right? So first of all, what is hunting? Hunting nothing but the sudden changes or vibrations in the rotor. When hunting takes place, then the damper winding produces the damping torque which eliminates the hunting. Yes or no? When the hunting will be produced in the machine, in synchronous machine, then the damper bars produces the damping torque. The damper bars produces the damping torque which eliminates the hunting. Right? So, which of the following is correct answer? Our damper bar produces the torque which is called as damping torque. This damping torque eliminates the hunting. What are the reasons for hunting, sir, actually? The sudden changes in load, the sudden changes in excitation, the sudden changes in supply frequency. These are the main reasons for hunting. When hunting takes place, our damper winding produces the damping torque which eliminates the hunting. Is 100% correct answer. Okay, sir, next one. Let's see. Next one. Per unit voltage of two synchronous machines connected through a lossless line. The given per unit values of two machines which are connected to a lossless line. One is 0.95 at an angle 10 degrees, and other one is 1.0 at an angle 0 degrees. 1.0 at an angle 0. 1.0 at an angle 0 degrees. Then match the following. Actually, the real power mainly depends on load angle delta, and reactive power depends on the EMF, excitation EMF, or simply excitation, or here EMF. Real power depends on delta and reactive power depends on EMF. Now tell me the real power of machine 1. Here machine 1 delta is greater than machine 2. Nothing but the real power flows from machine 1 to machine 2. Nothing but machine 1 delivering the real power. That's why this real power is positive only. This real power is positive only. Right. Next one. Reactive power of machine 1. Reactive power depends on excitation or EMF. This is less, this is more. Nothing but the reactive power flows from 2 to 1. Here active power or real power flows from first to second, that's why the P is positive. But here the reactive power flows from second to first one, that's why the reactive power of the first one is negative. The reactive power of the first one is negative. When it will absorb the reactive power, generally the machine when absorbs the reactive power under leading load. So the power factor of the machine 1 leading, and the reactive power of the machine 1 negative, and the real power of the machine 1 positive. Real power of the machine 1 positive. This is simply. For example, if they ask for machine 2, real power is negative, reactive power is positive, and it operates at a lagging load like that. So these are our question answers.